All right, today we're going to talk about something pretty fascinating, maybe even a little radical. It's an idea about how we pay for electricity, a mathematical approach that could, well, completely rewire our power grids. We're talking about making them fairer, sure, but also way more stable, especially as we look to the future.
So, just think about this for a second. What if? What if we've been paying for our electricity all wrong? Like, what if the entire foundation of our energy market is, I don't know, missing some huge pieces of the puzzle? That's the big question we're diving into today, because it really looks like our current system might be, well, dangerously incomplete. Okay, so to really get the solution, we've got to start with the problem. Let's break down what your electricity bill actually pays for, and, maybe even more important, what it totally ignores.
See, our current markets, they're really good at one specific thing, putting a price tag on a kilowatt hour of energy. Simple. A generator makes power, you get the power, they get paid. Seems pretty straightforward, right? But that's not the whole story. Not even close. The power grid is constantly doing all these other critical, honestly life-saving jobs in the background. It's got to be ready for a massive heat wave. That's what we call adequacy. It needs generators that can fire up in an instant when the wind suddenly stops blowing. That's flexibility. And it has to have power plants in just the right spots to stop the whole system from overloading. That's congestion relief. The problem is, right now, these essential services that literally keep your lights on are either barely paid for or handled through these really clunky separate systems. And that creates massive instability.
So, the big question is, how in the world can we build a system that pays a generator for its true value? I mean, all of its value to the grid. All right, let's get into it, because it turns out the answer might actually come from a field of math you wouldn't expect: game theory.
Let's use an analogy. Think of the power grid like a sports team, maybe a soccer team. You wouldn't just pay the striker who scores all the goals, would you? Of course not. You also need that star defender who stops the other team from scoring, or the midfielder who makes that one perfect pass that sets up the win. The grid is exactly the same. A battery that gives a quick jolt of power to keep things stable might be just as valuable in that moment as the giant power plant that runs 24/7. We need a way to measure every player's contribution to the team's success.
And that, my friends, is where this thing called the Shapley value comes in. It's actually a concept from game theory, developed way back in the 1950s. And what it does is pretty amazing. It gives us a mathematically perfect way to calculate the exact contribution of each player, or in our case, each power plant, to the total success of the group. Now, why is it considered so perfect? Well, economists love it because it nails 4 really crucial tests for fairness. First, efficiency. The total payout to all the players equals the total value they created together. Second, symmetry. 2 identical generators doing the same job get paid the exact same amount. Make sense? Third, the dummy player rule. If a generator contributes absolutely nothing, it gets, you guessed it, nothing. And finally, additivity. It all adds up consistently. And the key thing here? This is all based on pure physical performance. How much a generator actually helps the grid, not on some complicated bidding process or market games.
Okay, this sounds amazing, right? A perfect formula to create a fair, stable grid. So, what's the catch? Well, there's a catch. And it's not a small one. It's about the size of the known universe.
Here's the thing. To calculate the true, honest-to-goodness Shapley value, you have to run a simulation of the power grid for every single possible combination of generators being on or off. I mean, you test plant A all by itself, then plant B, then plants A and B together, then A, B, and C. Yeah, you see where this is going.
For a grid with, say, just 1,000 generators, which is pretty standard, the number of combinations you'd have to calculate is 10 to the 300th power. Let me try to put that number in perspective for you. It's not just big, it is a number so mind-bogglingly huge, it's bigger than the estimated number of atoms in the entire known universe. Yeah.
So as you can imagine, trying to run this perfect formula on any real-world power grid is, as the experts put it, computationally impossible. It's a beautiful idea in theory, but in practice, it's a complete nightmare. Or at least it was.
So this massive computational problem kind of forces us to ask a new question. What if we've been thinking about this the wrong way? What if you don't actually need to figure out the value of every single individual player? What if, instead, you could just figure out the value of the teams? And this is where the real breakthrough comes in, and it's actually beautiful in its simplicity. Instead of trying to calculate the value of 1,000+ individual generators, what if you group them into, say, 20 or 30 logical clusters? You group them based on where they are and what they do on the grid.
And just like that, the problem goes from literally impossible to totally doable.
Now, these clusters aren't just picked at random. They're based on the physical reality of the grid itself. Are these generators on the same major transmission line, the same power highway? Are they electrically close enough that one can easily cover for the other if it goes down? The whole point is to make sure that each cluster really does act like a single, coherent unit.
So here's how this nested Shapley process works. It's a really clever two-step shortcut. First, you run the Shapley calculation, but only on those 20 or 30 big clusters. That's a calculation a computer can actually handle. Step 2, once you know how much value each cluster or team brings to the table, you just divide that value up among the individual generators inside that cluster, usually based on their capacity. It's a simple, elegant way to make the impossible possible.
Okay, so we have all this elegant math, this clever shortcut, but what does it actually mean? What does this mean for the power plants, for the energy market, and at the end of the day, for your electricity bill?
What's really smart about this whole system is that it gets that different kinds of generators play different roles. So for your super flexible resources, think gas plants, batteries, the stuff that can turn on a dime, they compete for a payout from what's called the Shapley pot. Basically, they get paid based on how crucial they are during those moments of real stress on the grid. But then you've got the backbone of the system, your big nuclear and wind farms. They aren't really built for that kind of short-term competition. So to make sure they stick around for the long haul, for reliability and our climate goals, they get more stable, regulated payments. It's about creating the right incentives for every type of player on the team.
And that stability? Well, it works its way all the way up the chain, to you. Because when generators are paid fairly for their true value, the entire wholesale market becomes way more predictable and rational. Your energy supplier isn't just gambling on crazy price spikes anymore. And that newfound security frees them up to compete for your business on things that actually matter.
And really, that's the payoff for us, the customers. A stable wholesale market means your power company can stop focusing on just surviving market volatility and start focusing on you. They can compete on things like better product design, actual customer service, and, helping you find smart ways to manage your own energy use.
So when you step back and look at it, it's a really powerful idea. Who would have thought that a formula from the 1950s could be the key to building the resilient, clean energy grid we desperately need for the future? It all comes down to a simple concept: recognizing that every player has a vital role and making sure that every single contribution gets the fair value it deserves.